Hello students, today we are going to discuss the quantum mechanics topic, a very important topic. This is called quantum numbers. If I define in simple words, the quantum numbers are a complete address of an electron in the atom. So in order to find out the complete address of an electron in the atom, we need to find the four quantum numbers. The first one is called principal quantum number. It is represented by the letter N. The second one is orbital quantum number, represented by letter small l. Then third one, magnetic orbital quantum number ml. And fourth one is spin quantum number s. So let us discuss the first one, principal quantum number. So principal quantum number represents the main shell in which the electron is present. As we know that we have the positively charged nucleus, and the electrons are revolving in the orbits around this nucleus. Let us suppose this is one electron, second, third one, similarly this one. So since the electrons are identical particles, how can we differentiate between the electrons, or we can say what is the address of this particular electron or this particular electron? So in order to find out the complete address, we have four quantum numbers. So these are the principal cells, first, second, third. So this one is called K, L, M, and then we have N. For K, we have principal quantum number n is equal to 1. For L, we have n is equal to 2. For M, we have n is equal to 3. And for N, we have n is equal to 4. So if I make a table here, value of n, name of main shell, 1, 2, 3, 4, 5, K, L, M, N, O, and so on. So in order to understand further, we can take the example of hydrogen atom. We know that hydrogen atom has only single electron, and energy of this electron is given by minus 13.6 upon n square electron volt. Here n is principal quantum number. Let us suppose the electron is in the ground state. Ground state means n is equal to 1. The ground state represents n is equal to 1. Then E1 is equal to minus 13.6 upon 1 square, which is equal to minus 13.6 electron volt. Further, we can take the value of E is equal to 2. Minus 13.6 into 2 square. This is equal to minus 13.6 upon 4, which is further equal to minus 3.4 electron volt. E3. So these values come out from the value of n. If we put the value of n, we get different energies for different shells. So again, this is K shell. In case of hydrogen atom, if the electron is in the ground state, the energy level of this shell is equal to minus 13.6 electron volt. If the electron goes to the first excited state, that is n is equal to 2, the energy becomes minus 3.4 electron volt, and so on. So again I repeat, the n, which is called principal quantum number, represents the main energy of the energy shell in which the electron is present. If there are more than one electron present in a particular shell, the energy of those electrons is almost same according to this principal quantum number. So let us move to the second quantum number, which is called orbital quantum number, and it is represented by small l. It is very necessary to understand that these are only numbers and number have no units at all. So secondly, we have orbital quantum number n. So each shell is further divided into subcells. Each shell is further divided into subshells, and these subshells are represented by orbital quantum number. Let us suppose we have n is equal to 1, and for n is equal to 1 the value of L is 0. For n is equal to 2, value of L is 0, 1. For n is equal to 3, value of L is 0, 1, 2. From these three examples, we have value of L varies from 0 to n minus 1. For n is equal to 1, L is equal to 0, that is n 1 minus 1, further 0, n is equal to 2, from 0 to n minus 1, that is 2 minus 1 up to 1. Similarly, for n is equal to 3, from 0 to 3 minus 1, that is 2. So we have 3 values, 2 values, 1 value, and these L values are further given some names of these subshells. I can make the table here. Value of L, name of subshell, 0, 1, 2, 3, 4. For 0 we have S, P, D, F, G. Value of L is 0, it is called S subshell. Value of L is 1, it is called P subshell. Value of L is 2, it is called D subshell. So let us combine N and L value. This can give the electronic configuration of an atom. Simply, we have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. So this is the principal quantum number. This is the orbital quantum number. Principal, orbital, principal, orbital. You can see here the principal quantum number is same for these three subshells. For S, P, D, the value of N is same, but value of L is different here. So let us move to the third quantum number, that is called magnetic orbital quantum number. It is represented by Mn. Let me further clear about L. This value of L is connected to the orbital magnetic moment. Value of L is connected to the orbital magnetic moment. Orbital magnetic moment, mu L is equal to minus E upon 2m into n. Here L is orbital angular momentum, and its magnitude is L का magnitude है L into L plus 1 square root into h cut. So you can see that here h cut is equal to h upon 2 pi, everybody knows h is a Planck's constant. Right? So you have to remember this formula. We will use it in next few lectures. In here, the value of L is connected by this relation and value of mu L is connected by this relation. If I take the magnitude of mu L, if I take magnitude of mu L, we have E upon 2m into L, or we can put h hat here with this. This thing is combined and it is called mu B. This is called mu B. This mu B is Bohr magneton. Its value is 9.27 into 10 power 24 joule per Tesla. Okay, so this is called mu B. Its value is E h cut upon 2m, and the magnitude of mu L is equal to mu B under root L into n plus 1. You have to remember this formula also. We will use it further. So now let us switch to the third quantum number, which is called magnetic orbital quantum number. Basically, this quantum number represents the orientation of orbital quantum number L in the space around the nucleus. So the value of ml varies from minus L to plus L. If L is equal to 1, ml is equal to minus L to plus 1, that is minus 1, 0, plus 1. If I take L is equal to 2, we have ml is equal to minus 2, minus 1, 0, plus 1, plus 2. Okay, from the quantum mechanics, it is very clear that if I take the vector model, let us suppose this is the z-axis and the angular momentum L is oriented at an angle theta with respect to the z-axis, and the projection of L at the z-axis is called Lz. This Lz is z component of L, orbital angular momentum. Its value is Lz is equal to ml h cut. Ml is again orbital quantum number. So according to this diagram, we have cos theta is equal to Lz upon L. If I put the value of Lz, ml h cut upon, we have put the magnitude of Lz, which is equal to ml h cut here, and value of L, magnitude of L, which is equal to L into L plus 1 square root into h cut. So the orientation can be taken from this formula. Orientation of L can be taken from this formula. Let us take an example. If L is equal to 2, value of ml is equal to minus L to plus L, that is minus 2, minus 1, 0, plus 1, plus 2. Then orientation cos theta 1 is equal to let us put the first value minus 2 upon under root 6. cos theta 2 is equal to minus 1 by root 6, cos theta 3 is equal to 0, cos theta 4 is equal to plus 1 by root 6, and cos theta 5 is equal to plus 2 by root 6. So the value of ML gives the orientation of L in space. We have three orientations whose angles can be found from here: cos of theta 1 minus 2 by root 6, cos of theta 2, theta 3, theta 4, theta 5. It means for every value of L we have for every value of L we have 2 L plus 1 values of ML. For 2 we have 5, for 3 we have 7 values. For means for every value of L we have 2 L plus 1 values of ML. Or we can say that for every value of L we have 2 L plus 1 orientations in space for that particular electron. So let us switch to the last quantum number, which is called spin quantum number S. So we are going to discuss the fourth quantum number, which is called spin quantum number. Now we already know that electron is a fermion. Fermionic particle, and every fermion has half integral spin. There are two types of particles, bosons and fermions. Bosons have integral spin, fermions have half integral spin, and every fermionic particle obeys the Pauli exclusion principle. We have every fermion obeys Pauli exclusion principle. According to this principle, no two fermions can present in the same state unless they have opposite spin. I repeat, no two fermions can present in the same state unless they have opposite spin. So, what is spin? Again, we know that this is the nucleus, this is the orbital motion of, let us say, this point particle is a electron. Around 1925 or 1927, an experiment was performed which is called Stern-Gerlach experiment. From that experiment, it was concluded that the electron revolves around its own axis in addition to the orbital motion, and this motion, which is around its own axis, is called spin motion of the electron. And for that spin motion we have spin quantum number, and this spin quantum number combined with Pauli exclusion principle gives two values. S1 is equal to plus half, S2 is equal to minus half. Okay, in common we have S is equal to half, and corresponding angular momentum is called spin angular momentum, which is represented by vector S. As we have L is equal to under root L into L plus 1 h cut. Similarly, we have S is equal to under root S into S plus 1 h cut. Since the value of S is half, so we have S is equal to half plus 1 square root into h cut under root 3 by 2 h cube. This can also be represented by vector model. This is vector S, this is z axis. Its projection on z axis is called SZ, angle theta. So cos theta is again SZ upon S, or cos theta is equal to. So the value of SZ is given by ms h cut upon under root S into S plus 1 h cut. So we have cos theta is equal to ms upon under root S into S plus 1 h cut. So S1 and S2 is given a common name ms. ms can have value plus half, or ms can have value minus half. S has always half. So we have value of cos theta equal to plus half upon, we have solved it here, one by root 3, and if I put minus half, then I get cos theta minus 1 by root 3. So I repeat again, principal quantum number n gives the main shell in which the electron is present, and those shells are represented by k, l, m, n, and further each shell is further divided into subshells, and those subshells are given by quantum number L, whose value varies from 0 to n minus 1, and n varies from 1, 2, 3 up to infinity. It is an integer. If n is equal to 1, it is called ground state. Okay. So for values of L, we have names of subshells. For L is equal to 0, we have S. For L is equal to 1, we have P. For L is equal to 3, 2, we have D. S, P, D, F. Okay. So magnetic quantum number gives the orientation of L, whose value is given by minus L to plus L. It means the value of ML are 2L plus 1 values. The spin quantum number gives the orientation. According to Pauli exclusion principle, two fermions can only present in the same state if they have opposite spin. So the electron has spin quantum number plus half and minus half, and this spin motion was found in the Stern-Gerlach experiment in 1927. Okay. So with this we are finished with the quantum numbers. Let us recall about the magnetic dipole moment. I already told you that value of mu L is equal to minus P upon 2m into L. Its magnitude can be given as mu B under root L into L plus 1, where mu B is equal to EH cut upon 2m, which is called Bohr magnetone. Similarly, we have spin magnetic dipole moment mu s, which is equal to minus gs e upon 2m into s vector. Here gs is spin g vector, which comes from the experimental values. Its value comes out to be is equal to 2. Here also we have minus GLE upon 2 into L. Here the value of GL is 1, but here the value of GS is 2. So we can say that value of mu S is equal to minus 2 E upon 2m into S. Again, if I put the value of S here in magnitude, minus GS E upon 2m, we can remove the negative sign if I take the magnitude. S into S plus 1 h cut, I combine this H cut here. Again, this is Bohr magneton. So we have value of mu s in magnitude is equal to gs mu b under root s into s plus 1. So thank you students. With this we are finished with the quantum numbers, 4 quantum numbers, a complete address of the electron. So thank you very much.